Hi everyone, welcome to our discussion today. My name is Daphne. Today I'm going to discuss the development of my project, a root finding app designed to help students and professionals easily find roots of complex mathematical equations. We'll delve into the app's features such as graphical method, incremental method, bisection method, regular falsi method, Newton-Raphson method, and second method. First, we're going to discuss the graphical method. Graphical method. Imagine you have a curve that represents your function, f of x. The roots are where the curve crosses the x-axis where f of x equals 0. To find these roots visually, you need to draw the graph over a specified interval. If the graph goes above the axis and then below it, or vice versa, the root is somewhere in between. The plot itself helps you see where to look more closely. The first line is x-vals. This line generates 400 points evenly spaced from x-min to x-max. This creates a smooth curve. While the y-vals calculate f of x for each of these points. Basically, get the height of the function at each x. The plot figure. This line prepare a new plot figure to draw on. The PLT plot, it's the code that plot the function f of x with x on the horizontal axis and f of x on vertical. The x line is a code that draw a horizontal line at y equals 0 to represent the x-axis visually. If you already have approximate roots, mark them as black dots on the x-axis. This code also add title, grid, legend, and show the plot. Graphical method is the code logically creates a visual that helps you see where roots might be by plotting the function and highlighting points near 0. Now, let's go to incremental search method. This method walks through the interval from x lower to x u in small steps, checking whether the function value changes sign between each pair of points. A sign change means the function crossed 0 in the subinterval, so a root exists there. It's like feeling for the root by checking if you step up from the positive to negative or vice versa. This code intervals. It is this code that starts with an empty list to store intervals where roots are suspected. The x current is initialize your walking point at the start of the interval. While x current, it loop until you reach the upper bound. The x next equals x current plus delta x. It moves forward by small step size delta x. If you step up past the upper bound, dump it back to x of u. It multiplies f of x current and f of x next. If the product is negative, the function changes sign. Save this interval because a root is between these 2 points. Move the current point forward to continue checking. Return all intervals suspected to contain roots. Incremental method is a code walks along with the interval in small steps, testing for sign changes and records all subintervals where roots lie. Now, let's go to the bisection method. You have a bracket x of L and x of u where f of x L and f of x u have opposite signs. Bisection finds the midpoint xr equals x of L plus x of u divided by 2. It checks which half contains the root by testing signs. It then replaces the bound with the midpoint to shrink the search interval by half. This repeats until the error is small or function value near zero. This line, the data, it prepare a list to save iteration details. The second code is XRO none is the code that keeps track of previous root approximation to calculate error. For I in range code 3, it looked up to max iterations. These following codes are the ones who compute midpoint, XR, evaluate f of x lower, and f of x r. This code also calculate approximate relative error, E of A, if possible. The code also have checked if root found by testing if f of xr is very small. Then it save iteration data to show progress. It stop if root found. It also update interval bounds depending on where root lies. If sign change between x of L and x of R, root is in left half, so set xu equals xr. Else, root in right half, so set x of L equals x of R. Update previous root estimate for error calculation next iteration. Columns equals iteration xl. Is a code that converts saved data into a table for display. Bisection is the code systematically narrows the interval by splitting in half and choosing the subinterval containing the root. It tracks errors and stops once the root is found within the required accuracy. Now, let's go to regular fallacy. Regular fallacy improves in bisection by drawing a straight line between x of L, f of xl, and f of xu, then finding where the line crosses the x-axis. This xr often approximates the root more accurately than the midpoint. Then update the interval as in bisection based on sign change. Regular fallacy. This code is evaluate f of xl, f of xu. It calculates denominator f of xl minus f of xu. If zero, error because the division not possible. Compute new xr using the false position formula. It evaluates f of xr. It checks product f of xl times f of xr to know which side contains root. Update x of L or x of u accordingly. This code also saves iteration info. It also stops if root found. Regular fallacy is a code uses a linear approximation to find a better root estimate. Updates the intervals similarly to bisection and tracks error and conversions. Now, let's go to Newton-Raphson method. Newton-Raphson uses the derivative to find the tangent line at the current gas and find where this tangent crosses zero. This gives the next gas. Starting from initial gas x of 0, the formula x of 1 equals x of 0 minus f of x0 divided by f of 0 gives the next approximation. This usually converges quickly if the gas is close. The Newton-Raphson method code it calculates f of x0 and derivative f of x0. It checks derivative is not 0 to avoid division by 0. It computes new gas xr. The code also calculates error or EA. It checks if function value near 0, root found. The code also saves data and update gas to new root. Newton-Raphson code applies the Newton-Raphson formula repeatedly, checking errors and derivative validity until convergence. Now, let's go to the second method. Second method is like Newton-Raphson, but approximates the derivative using the 2 points instead of exact derivative. It starts with two initial gases, x of 0, x of 1. Next gas computed by formula similar to false position. By the given formula. Next, the code also it doesn't need explicit derivatives. And it repeats with updated gases until convergence. The second method also, this code compute function values of x0 and x1. Next, it uses second formula to get next root approximation. This code also calculates error relative to a previous root. It stops when error less than tolerance or max iteration reached. The code also updates gases for next iteration. So, second method approximates the derivative with 2 points, repeatedly refining the root gas without needing explicit derivatives. So let me show you the root finding app in its design and how it works.